Hey guys, Mr. O'Sullivan here. Hey, I'm going to start talking about our new pre-response topic, and that would be related rates. We're going to take a look at the related rates problem from 2019. It was number 4, no calc problem. And so here it goes. We're given a diagram of a cylinder. So reading the question, the cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown in the figure above. Water drains out through a valve. It's not shown at the bottom of the barrel. The rate of change of the height h of the water in the barrel with respect to t is modeled by dH dt is equal to negative 1/10 square root of h, where h is measured in feet and t is measured in seconds. The volume of a cylinder with radius r and height h is v equals pi r squared h. And then we're asked to do 3 things. Find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet, indicate units of measure. B, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. And then part C, at time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. All right, so as we dive in, we're given a differential equation there, dH dt is equal to negative 1/10 square root of h. And they're going to ask us, part A, find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet, indicate units of measure. All right, so one thing we might do is, as much as we can, convert the words into calculus notation. So in part A, we're asked to find the rate of change of the volume of water in the barrel with respect to time. Now the calculus for that, rate of change of the volume of water, is dV dt. So that is what we're asked to find in part A, when the height of the water is 4 feet. So basically, we're looking for dV dt such that h is equal to 4. And we also want to make sure we indicate the units of measure. There's going to be a point given for units in this problem. All right, well, to come up with dV dt, we are given the formula for the volume of a cylinder. So if we start with that, V is equal to pi r squared h. And then if we take the derivative with respect to time, both sides of our equation, we get dV dt is equal to pi. And now we're going to need the product rule. So I'm going to call r squared u hv. And so I'm going to have u prime is going to be 2r dr dt. V prime is going to be dH dt. So the product rule tells me it's going to be u prime, 2r dr dt times v times h plus u v prime. U is r squared, v prime is dH dt. So now I have an equation that gives me dH dt, and in terms of r dr dt, h, and dH dt. So I'm told dH dt is given as negative 1/10 square root of h. So I'm just going to drop that in. I am told I have to remember that h is equal to 4. So I'm going to drop in 4 for h. My diameter is 2 feet, and so my radius r is equal to 1. So r is equal to 1, so 2 times 1. Now, dr dt, it's important to note, dr dt in this example is equal to 0 because the only thing that's changing in this scenario is the height of the water. The radius, the cylinder itself, is not changing. So dr dt is going to be equal to 0. So that's actually going to simplify my calculation quite a bit. Plus r is equal to 1 squared dh dt dv dt is equal to that. And I'm given dh dt is equal to negative 1/10 square root of h. Negative 1/10 square root of h. H is given as 4. So this is going to zero out. Times pi. And so my answer is going to be dv dt is equal to negative pi times 2/10, or negative pi over 5. Now, I want to make sure that I do include units. And if this is the change in volume, and volume is measured since the height is given in feet and the radius or the diameter is given in feet, so the volume is going to be cubic feet. And my rate of time is given, I look for T is measured in seconds. So that would be cubic feet per second. All right, so there's part A. And after we complete this, we'll go ahead and score this as well. Part B, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. Okay, so the rate of change of the height of the water with respect to time is given by dh dt. So dh dt is given by negative 1/10 square root of h. And they're asking me to make a determination, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. Now, I'm not asked to come up with and determine whether the height of the water is increasing or decreasing when the height of the water is 3. That'd be pretty simple. I would just go through and I would just take dh dt when h is 3, plug that in, and I'd get negative square root of 3 over 10. And I'd say, well, that would tell me that the height of the water is decreasing. They're not asking for that. They're asking for, is the rate of change of the height of the water with respect to time increasing or decreasing? So what I need to do is I need to come up with the derivative of dh dt. So I want to find ddt of that. So I'm going to come up with the second derivative is equal to negative 1/10. I'm going to just rewrite this. Think of that as h to the 1/2. So it's negative 1/10. If I just do the power rule on this, that's going to be times 1/2 h. And if I subtract 1 from that, I get to the negative 1/2. Then I have to remember times dH dt. I have to remember chain rule on that. All right. So what I can do is I'm asked to find the rate of change of the height of the water. I'm asked to find if that's increasing or decreasing. So I'm looking at the second derivative. Now if I just write this, negative 1/10 times 1/2 times h to the negative 1/2. And then I'm just going to drop in for dH dt what I'm given, which is negative 1/10 square root of h. So now I want to know d2h dt such that when h is equal to 3, so I drop this in, I have negative 1/10 times negative 1/10, that's going to be positive. So I'm going to have positive 1/10 is 1/2 times 1/10 times really square root of 3 over the square root of 3. Well, I don't even really care what this is. The only thing I care about is that this is going to be some positive number. Therefore, what I like to do is just kind of phrase the question back to them, but I can see since this is positive, it's going to be increasing. I'm going to say the rate of change of the height of the water with respect to time is increasing when the height of the water is 3 feet. So the rate of change of the height of the water with respect to time is increasing when h equals 3. Again, you can imagine a pretty common mistake with this problem. These students would have just said, oh, gee, this is as easy as it gets. I just need to take dH dt, substitute in 3 for the h, look at the sign of that, it's going to be some negative, and so therefore it's going to be decreasing. Well, that's not correct. Okay, last part. Part C, at time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. Okay. So if I drop this right here, so I'm given at time t equals 0 seconds, the height of the water is 5 feet. So this is basically an initial condition that tells me that h at 0 is equal to 5. And what I want to come up with is an expression, an equation for h in terms of t. So this is, we're kind of changing gears, going from a related rates problem in part A and B to now we're going to a differential equation problem in part C. So I want to start with my differential equation. dH dt equals negative 1/10 square root of h. That's going to be my starting point. So dH dt is equal to negative 1/10, and I'm just going to do a rewrite. Square root of h is going to be just h to the 1/2. Should be negative 1/10 square root of h. All right, so I'm off to the races. First thing I want to do, most important, I want to separate the variables. As we've always stressed, this is the most important thing most important step of this differential equation problem. So if I separate the variables, what I can do, I'm going to move the h to the 1/2 to the other side of the equation, and I can treat that. I'm going to leave the dh over there, and what I can do is just treat that as h to the negative 1/2. And if you think that through, again, that's the negative would mean that I would have 1 over h to the 1/2. In essence, I've divided both sides of my equation by h to the 1/2. So that's the left side of my equation. I'm going to bring the dt over to the right side. And so I'm going to have negative 1/10. Leave that constant right where it is, dt. Okay. So separated the variables. I'm ready to integrate both sides. So I integrate the left side. I'm going to have h. I'm integrating, so I'm going to add 1 to that. So that's going to be positive 1/2. I divide by 1/2, which is the same as multiplying by 2. So I get my antiderivative on the left side is 2h to the 1/2 is equal to negative 1/10 t, and then add my constant of integration plus c. Okay. At this point, I want to just copy what I've got. 2 raised to the 1/2 is equal to negative 1/10 t plus c. And now what I'm going to do is I'm going to substitute in my initial condition, h at 0 is equal to 5. So I'm going to have 2 times square root of 5 is equal to negative 1/10 times 0 plus c. So c is going to be equal to 2 square root of 5. That's the value of my constant of integration given this initial condition. So I've got 2 h to the 1/2 is equal to negative 1/10 t plus 2 square root of 5. And now I just have to solve for h. So I'm going to divide both sides. 2. Get h 1/2 is equal to this hot mess. So it's going to be negative 1/20 t plus square root of 5. And my last step, I want to square both sides. I'm going to get h is equal to squared. And so that is my equation for h in terms of t, given that initial condition. All right, let's go ahead and take a quick look at the scoring guidelines for this, see how we did. All right, so part A, we got negative pi over phi cubic feet per second. And this was worth 2 points. So at some point we had to show that dv dt is equal to pi times dh dt. And so I've got that point kind of shown right here. So 1 point for that. And then 1 point for my answer with the units. So negative pi over 5 cubic feet per second. So we're 2 for 2, feeling pretty good in part A. Part B is worth 3 points. So I've got to show that first part is I've got dh dt is equal to my negative 120 square root of h. So I have this right here. 1 point right here for this. Second point is going to be the where we remember to substitute in for dh dt. So we have this times that. So this is the second point right there. And then the third point is going to be the answer with the explanation. The rate of change of the height is increasing when the height of the water is 3 feet. And that's what we've said, that it's increasing. So we got 1 point for that. So we are 3 for 3 on part B. And last but not least, on part C, we're going to get 1 point for the separation of variables. Going to get 1 point for the correct antiderivatives here and here. 1 point for the constant of integration. And plugging in the initial condition. So that's 1 point here, and then also 1 point for plugging in our initial condition. And then last but not least, 1 point for h of t, which is equal to negative 120t plus the square root of 5 squared. So 1 point for that. 1, 2, 3, 4 points on part C. Again, 0 for 4 if we don't do correctly the separation of variables. Okay, guys, hope that helped. Thanks.